Okay, so yes, if you want Maple, you can get it for free. Okay. Hope everything is working now. Can you hear me? Hope it's okay. All right, so let's see where we are. I'm interested in solving this congruence, x to the power 17,389, congruent to 43,927, modulo this very large number, which is a product of two primes. And the first thing to do is to solve the congruence. So what is phi of n? Phi of n is 229 minus 1, 228, times 281 minus 1, 280, which is equal to what? 228 times 280 is 63,840. So I want to find, this is my exponent E. I want to find a number D such that 17,389 times D is congruent to 1 mod 63,840. And this takes a little bit of work, but if you solve the congruence, you get D is any number congruent to 53,509 mod 63,840. So the solution of this congruence will be X congruent to C to the D this is my C, 43,927 raised to the power 53509. Only a computer can do this, really. Well, it's not quite true, but it's hard. 14,458 modulo 64349. So this is the congruence we want to solve. This number to this power congruent to this, mod this. And this number is relatively prime. This is my E, it's relatively prime to N, P times Q. And the solution is this. Right? Now,
Professor, can you show in the maple, like again, the commands are like exponent,
well, in
comma, base,
Maple,
comma.
there's a command called is prime N, and it gives you an answer, either true or false. True if N is prime, false if N is composite. And there is a command I factor N, which writes N as a product of primes. Those are the only two commands that I just showed.
Okay, thank you.
But there's a very useful feature in Maple called help. And if you go to help and you type in factor or prime, you will be led eventually to these commands.
Thank you.
Okay. Okay, so this is all background for describing the RSA crypto system. And this is an example of what is called a public key crypto system. This means that everyone in the world is told the method to encrypt a message. It is public. If you're sitting at CIA headquarters in Washington and someone wants to send you a message, they know how to encode it. And the crux of this, the key idea of this method, of this sort of philosophy, if you like, is that it's possible to construct a crypto system in which everyone knows how to encrypt a message and send it, and whoever intercepts it, but you're the only one who can decrypt it, who can decipher the message, right? So the key for encryption is public. Anyone can encrypt a message, but only the receiver knows how to decrypt it. So this is really an amazing idea, and the fact that it is possible is quite extraordinary. So in our system, there's Bob, and there's someone out there named Alice, and Alice wants to send a message to Bob. So send message to Bob, but it has to be an encrypted message. So Alice wants to send a message to Bob, and it will be an encrypted message. How does she encrypt it? So here is the key creation. So Bob creates a public key as follows. Bob creates a public key as follows. So Bob chooses 2 primes that are secret, P and Q, distinct odd primes. And Bob also chooses the encryption exponent, E. And so, and E has to have the property such that the GCD of E and P minus 1, Q minus 1 is equal to 1. And what Bob publishes and tends to the world is the number N, which is P times Q and E. So what is public is a number N and a number E. Okay. Now, everyone knows N, but they don't know P and Q. If they can factor N, they can find P and Q, but the idea is that it is hard to factor. In any case, Bob publishes the product of his 2 primes, but not what the 2 primes are. So what is the encryption algorithm? Alice wants to send Bob the message M. So M is some number, right? But that's the plain text. But she doesn't want Eve, the interceptor, the spy, the enemy, to know what M is. So she has to encrypt the number M. So let you calculate m raised to the power e mod n. And that let C be congruent to m to the e mod n. So this is how you encrypt your message. This is the ciphertext. C. Everyone knows E, everyone knows N. The message Alice wants to send is M. She takes M, raises it to the power E mod N and reduces it mod N, and she gets a number C. And what she sends to Bob is this number C. That's the ciphertext. Okay? And Eve, who is eavesdropping, can intercept the number C, right? Okay. Well, how does Bob decipher C? What does Bob do? Bob can solve the congruence ED congruent to 1 mod P minus 1 Q minus 1. Bob knows P and Q, so he knows P minus 1 and Q minus 1, and he chose E to be relatively prime to this number. So by the elementary facts of congruences, you can solve the linear congruence. You can find a number D such that ED is congruent to 1 mod P minus 1 Q minus 1. And then Bob computes the number, let me call it M prime, which is C to the D mod N. C is the number that Alice sent him. D solves this congruence, right? So what is this? C is M to the E mod N. So this is M to the E to the D, which is M to the ED mod N. And ED is 1 plus this, so this is M to the 1, or M, times M, the sum multiple of P minus 1 Q to the minus 1. M to the P minus 1 Q to the minus 1 is 1. So this is just M mod N. So Bob has deciphered the message. Right? So let me do an example with numbers so we can kind of see what it is that's going on here. Let me try and find an example in the text. So we start with Bob. The first thing Bob does is choose 2 primes. So suppose he lets P, the first prime, be 1223, and the second prime be 1987. So Bob knows P and Q. He doesn't tell anyone. But then all he does is multiply them together. And when you multiply them together, you get the number so Bob picks his 2 primes, 1223 and 1987. They're secret. He doesn't tell anyone. He multiplies them together. He gets this number, 2,430,101, and he publishes this to the world. He tells everyone in the world N is 2,430,101. Right? Then Bob chooses the encryption exponent. This is public. Everyone's going to know it. The public encryption exponent E equal to 948047. And he chooses the exponent such that he knows that the GCD of E and P minus 1 times Q minus 1. So that's the GCD of 948,047. And the product of these two numbers, P minus 1, Q minus 1, which is 2426, 892, equals 1. And the other, so the other number that Bob publishes to the world is this exponent, 948,047. So these are public. Everyone knows these, not just Alex, but everyone knows those two numbers. And because he's going to be able to, he needs to be able to decrypt a message. Bob then computes an integer D such that D times E or E times D.
Alice will.
Sorry? E times D is congruent to 1 modulo P minus 1 times Q minus 1. And a number E that works is, so the number D has to satisfy 948,047 times D congruent to 1 modulo 2,426,892. And the number D with this property is 1,051,235. So this is, but only Bob knows this, and Bob knows it because he knows P and Q, so he knows P minus 1 and Q minus 1, and he can solve this congruous. So Bob has done all of this. The numbers he publishes to the world are just N and E, not P, not Q, not D. Okay. Now Alice wants to send Bob a message. The message she wants to send is the number 1,070,777. So what does she do? She computes C, which is going to be M to the E mod N. That is 1,070,777 raised to the encryption exponent 948,047, and that number reduced modulo capital N, which is 2,430,101. And when you do this calculation, the number she gets is 1,473,513. So this is the number Alice sends to Bob. So Alice wants Bob to get the message 1,070,777. That's the plain text. And the encrypted number is this. This is the ciphertext. So Bob receives this number from Alice. And what does he do? Bob computes C to the power D mod N, which is, I mean, these are big numbers, not huge, but big numbers. 1,473,513 raised to the power 1,051,235 and reduced modulo n 2430101. Anyone who has D can decrypt the message, but only Bob has D. And if you do this calculation, you see that in fact you will get 1,070,777. Okay. Now, why is this okay? Why does this actually work? Well, partly it's a matter of belief and experience and not proof. You see, in order to decipher the message, you have to know that this number n, which is a product of two primes, can be factored. It is a product of two primes, but how do you find them? You're given this number, you know, Bob is happy for you to know, this is a product of two primes. What are they? It just seems to be the case, no one knows why, that factoring is difficult. Why is it difficult? I don't know. No one knows, but it seems to be difficult. At least no one has come up with an algorithm for factoring that does a factoring problem in a reasonably short amount of time. You can try every single possible integer from 1 up to this number, do division, and see if what you get. This is actually, it's only 2 million. That's a relatively small number. A computer will factor this number just by exhaustion. But a number with 100 digits can't be factored by exhaustion. There just are too many possible divisors.
Question.
Yes.
What is the easiest way to find D?
Well, for solving this congruence, one thing that you can always do is, you know that these two numbers are relatively prime. So you can use the Euclidean algorithm to find D. And then when you reverse the Euclidean algorithm, you'll get D as a linear, you'll get 1 as a linear combination of these two numbers. That was the whole reason why we spent so much time on the Euclidean algorithm and writing. Remember, in the Euclidean algorithm, you write the GCD of two numbers, A and B, in the form AX plus BY. So if A is D and B is M, then this is DX plus MY, and this is equal to 1. So dx is congruent to 1 mod m. This x, sorry, E and m. So this x is your D. Your solution of this equation, which you get from the Euclidean algorithm, will give you this D. And there are other ways to do it that are a little bit faster, but that way will always work. I mean, it's no different from asking, how do you solve the congruence 3x congruent to 1 mod 19? Well, there's trial and error, or there are other ways also, but it's the same problem, right? Or except now we're using D as the variable, 3D congruent to 1 mod 19. So this is something times D, ED congruent to 1 modulo this. That's how you do it. And it can take some time, but a computer can also do it for you, usually. Okay. That is our essay. Now, It's hard to break this code, right? So Eve, the enemy,
Professor,
yeah,
you say it's hard to break it.
yes.
What make it hard?
The fact that you cannot factor this number into a product of primes.
Uh,
Right.
okay.
That is, everyone knows N, everyone
Sure.
knows E, everyone knows C. But
Okay.
to get from C back to M, you have to know this number D. D is a solution of this congruence. You can, you know E, you know N, you know P times Q, but you don't know P minus 1 times Q minus 1. If you could factor N to find P and Q, then you would find P minus 1 and Q minus 1, and you can solve this congruence. So the difficulty in RSA is the difficulty in factoring a number. If you can factor a number, you can break this code. This is a 7-digit number. That's trivially small. It's large for pencil and paper. It's trivial for a computer, right? But you take a 100-digit number, it's not trivial for a computer. It's almost impossible. Take a 1,000-digit number, forget it, it's hopeless. So it's the difficulty of factoring that makes RSA a reliable crypto system. If someone comes along and figures out a fast way to factor a number, RSA becomes useless. Anyone will be able to break it. In fact, there
I will
is,
try.
yeah, go ahead. Question? In fact, there is an algorithm for factoring a large number that works very, very fast. The problem at the moment, it's just a temporary problem, is that it is a quantum computer algorithm. So you need a quantum computer to factor a number. So one can just make this remark. There is a quantum algorithm for factoring. Unfortunately, or fortunately, do not yet exist. Right? So there is a quantum algorithm for factoring large numbers. Unfortunately or fortunately, quantum computers do not yet exist. A huge amount of money and research time and intellectual effort are going into trying to design, engineer, build quantum computers. And the ones that do exist so far are very, very, very weak. So they're not yet strong enough to do anything like factoring. I have no doubt that at some point quantum computers will be developed large and far enough along so the factoring algorithm can be implemented, but it hasn't happened yet. Once it happens, RSA is worthless and no one will use it anymore. That's just the nature of that. Now, this is a course in cryptography in terms of the mathematics that underlies the crypto systems. But it's interesting to try to figure out if you're Eve and you want to steal So if you're Eve and you're trying to steal the messages being communicated, the things you could try to do, even if you don't know how to break the code directly. But what I see happening is my computer or my internet, something is clunking out over here and I'm constantly being forced off the internet. So what I think I'm going to do is stop at this point, and I will, when my internet is more stable, I'll record a lecture this afternoon or this evening and post it on archive, post it on YouTube. So it has the material that I So that's all I can do today because my internet is just switching on and off. I'll record a lecture and post it on YouTube. And that's it for today.